Great. Okay, my apologies to the people listening in on the recording because I forgot to record any of that. So what you missed was us showing you, if you have the example of the map H from linear polynomials to linear polynomials, then we find the image of the basis vectors here, 1 plus x, 1 minus x. We represent them in terms of the standard basis 1 over x here and get this is 1, 1, this is 1 minus 1. That gives us our matrix, 1 minus 1. And then we can see how it acts, its matrix action to act on 5, 3 to give us 8, 2. And then see how this vector over here, column vector, is the representation of a polynomial vector. And we can just go back and forth between the vector and its representation. Okay. So now this was simple because we used the standard basis, but if we used a different basis, then we have to do all that rigmarole with changing, it would be different representations. Does this give you and then we can ask, well, look, we have the matrix H here. We can take minus row 1 plus row 2, 1, 1, 0, minus 2. So we can see the rank equals 2, right? But since the 2 plus the nullity has to equal 2, the dimension of the domain, the nullity equals 0. So it is, this map is onto and 1 to 1. Okay, so what shall I do next? Anyone have a thought?
Just a refresher. Okay, the rank of the map, if it's equal to
The rank of the matrix.
Yeah, but so if it's equal to the dimension of the domain, then it's 1 to 1.
If the nullity is equal to 0.
Right, if the nullity is 0, it's 1 to 1, but for onto
if it's onto, the rank has to equal the dimension of the codomain.
Codomain.
So the dimension here, the dimension of W equals 2 also, because W equals P1. So if I had mapped like linear polynomials to quadratic ones, then obviously it's not going to be onto, right? And if I had mapped quadratic polynomials to linear ones, it could be onto, but it's not going to be 1 to 1. So it's so that if the dimensions are different of the domain and codomain, you know certain things that can't be, might not know the values, but you already know that it can't be either 1 to 1 or onto, but if they're the same, anything goes. If the dimensions are the same. So then you have to do this. Okay. Let's see. So another example, or what do you want to do now?
Looking to see if there's anything on homework that was.
Oh, well, there is, let's see. You can also find whether a square map is singular or not by finding its rank, but let's look at the homework. Yeah, how about that? And see assignment. Okay, let's look at the homework. So these are early stuff, right? This is just the range. This is before you get to matrices. And then let's see, that's before. Okay, so here it is. Number 7. Consider the map P2 to P1 given by A plus BX plus CX squared. Let's look at the PDF of this so you can just see what the. Okay, so number 7. 6 is okay. 7 is okay. You have the. You have a polynomial map quadratic to linear. No, wait, what am I doing? Okay, it's not quadratic to linear. There's a typo there. This is obviously quadratic to quadratic. I'll have to fix that. And what is the image of the so that we have what is the image of the standard basis elements of P2? So we want to find the image of 1x and x squared. So we use this formula to find the polynomial. Okay, then what is the matrix which implements this map with respect to the standard bases for domain and codomain? So then we take that image and represent it as a column vector. And that would, each one of these images would be the column vector. That column vector would be the first, the image of 1 under this map made into a column vector would be the first column of the matrix. The image of the x that you get from this formula made and represented as a column vector would be the second column of the matrix, and the same for this one. So you get the matrix, and then you can check that your matrix is correct by saying, well, let's use this formula to find what this one is, but then represent this as a vector, multiply your matrix in, you'll get an answer, and then it should then translate back and you should get the same vector. So this is just sort of a sanity check that you understand how to go back and forth between polynomials and representations. Okay. Number 8. Okay, it's like R2 to R3, and that's correct. I'm giving you the basis action, 1, 0 to 2, 2, 0, 0, 1 to 1, 1, 0. Use standard bases for both spaces. Find the matrix which represents this map. Also find the general formula for H of V for some vector X and Y. Okay, so then you're going to find the matrix that represents this map of the standard bases. And then here is number 9. I'm given the basis action of polynomials from P2 to P3. So for P2, I have 1x and x squared using standard bases for both spaces. So for P3, it'd be 1x, x squared, x cubed. And you find the matrix that represents this map. Then 10. Here's one where you have R3 to R2, right? And you have an unusual domain basis and a codomain basis here, which aren't the standard ones. So what you do is you're going to look for the image of this one under this map, the image of this one under this map, the image of 1, 0, 0 under this map. And then what you get is going to be in the standard basis. So then you have to take each one of those and write them as a linear combination of these, and the coefficients in that expansion will be the matrix elements that you're looking for. So you should be able to. So everything now is none of this stuff is, once you wrap your head around it, this stuff is actually easier than a lot of the stuff we've done before. And you'll be happy to see that we've given up on proofs, right? Okay, well, so I think that you should be able to We should be able to, let's see, where does this go? This goes under assignment 5, okay, there. So well, let me